Good morning, class. Today we're going to take a look at our Laplace table and see how we can form the inverse transform. So in other words, we are going to be starting with capital F at S. So one of these functions of S, and performing the inverse Laplace transform in order to figure out little f at t. Okay, so this is a little more challenging than the reverse process that we practiced yesterday. So let's get started. I'm taking examples right from your textbook. Again, this is 31.11. Here's our first example. It's problem 22. Okay, so we have capital F at S equals, and we're given this fractional expression. We actually should always start with the denominator. So you're looking in the capital F at S columns for a denominator like this. But if you scan these quickly, you'll find that there is no trinomial in a denominator here. So what we can do is look to factor this denominator. Now, it is a trinomial with a leading coefficient of 1, which means that if it's factorable, it's very easy to factor. So if it's factorable, the factors would be of this form. Now this is s to the 4. Usually we would have s squared here and we'd put an s there and an s there. Here we have s to the 4. So we're actually going to have s squared here and s squared here like this. And then what do? Well, we simply say that we need a product of 1 and a sum of 2. So a product of 1 and a sum of 2 means the numbers are both 1. Just like that. Okay, so if you want, you can write here, we wanted a product of 2 and a sum of 1, and that means the numbers were both 1. So we end up with this, s squared plus 1 times s squared plus 1. Now, before continuing, because these problems are lengthy and you don't want to make a mistake early in the game, you would check this, right? So do your first, outside, inside, last, collect the middle two terms. Make sure that when you multiply these two binomials, you do in fact get this trinomial back. Okay, now though, this is s squared plus 1 all squared. So we would change that before continuing. So now we've got s squared minus 1 in the numerator. The denominator is now the square of s squared plus 1. All right, so we've changed the appearance of the denominator. Now what you do is you take a look at your capital F at S columns. Where do we see this denominator? I think you'll find that it is here, s squared plus 1 all squared. And here, s squared plus 1 all squared. And here, s squared plus 1 all squared. I guess also here, s squared plus 1 all squared. So these four have a denominator that compares very well with ours, of course, with a being equal to 1. So now we have to figure out which numerator is correct. So now that we've narrowed down the denominators, now look, we're saying that a is equal to 1. So for our numerator here, look, s squared minus 1 squared. So this one is a perfect match, number 18. So I'm going to write here that we have a match to number 18 with a being equal to 1. Okay, because again, 1 is the same as 1 squared. So we have 1 squared here, 1 squared here as required. Okay, so we've got a perfect match to number 18. So now all we do is we change the left-hand side to f at t, and we write here t cosine of 1t. So f at t, little f at t, is t times the cosine of t, and we're done. Okay, so first deal with the denominator. Once you've got the denominator established, right, and we had multiple possibilities here, but if you look at this would just be 2 times 1, so that's not this numerator. This would be 2 times 1 times s, certainly that's not this numerator. This one is also 2 times 1, but times s squared, and that's not this numerator. So the correct numerator is here. All right. Let's go ahead and look at our next problem. So here's our next problem. Problem 24 is the next one I'd like to do. Again, start with that denominator. It's a trinomial. There are no trinomials in our denominators here. Can this one be factored? Well, again, it's got that leading coefficient of 1. But if we were going to factor this, we would need a product of 13 and a sum of 4. And you should know immediately that that's not possible. So this guy is not factorable. So we have to change the denominator without factoring. In fact, if it's not factorable, so if it was factorable, of course it would look like this when we were done, right? It would have been a 9 or a 10. Okay, so unless it was a perfect square, then it would have been this kind of a denominator here, right? Okay, but it's not factorable. So all we can do is try to make it look like this. And how do we do that? We use completion of the square. So how do we complete the square? Well, we take this trinomial and we change it into this. So the first two terms stay the same, s squared plus 4s. Then you put the magic number here. You might remember this. We've done this before. How do you form the magic number? You take the coefficient of s, which is 4, and you divide it by 2, and then you square it. Okay, so the magic number is going to be formed by taking 4, dividing it by 2, and after dividing it by 2, you square it. So what does that give us? That gives us 2 squared, which is 4. So the magic number is 4. So we put that magic number there. Okay, so now we have s squared plus 4s plus 4. But here we have 13, not 4. What is 13 minus 4? 9. So all we've done, look, overall, all we've done is we've taken 13 and we've made it the sum of 4 and 9. Okay, why did we do that? Because again, we're going to get it to look like the denominators here. So now we take this part and we factor it. Okay, so once you've used completion of the square, this trinomial is always a perfect square. Okay? So product of 4 and sum of 4, the numbers are both 2. So this trinomial is the square of s plus 2. Check it, right? You could check it by multiplying s plus 2 and s plus 2, and of course you'd get this trinomial back. So you take the trinomial that results, it's always going to be a perfect square, so you'll always write it like this. And as for the 9, we want it to look like this, So we change it to 3 squared. Okay, and now we've got this denominator exactly. Our a value is 2 and our b value is 3. Okay, so we've got the 19 and 20 thing going on with a equal to 2 and b equal to 3. Okay, so take a look now at the numerator. Now that the denominator is set, look at the numerator. It's s plus 3. So it looks like it might be this match. But remember, a is 2, so this is actually s plus 2. S plus 2. So we can only use transform 20 if the top is s plus 2. So what do? We make it so. We split it now. So we'll have s plus 2 in the numerator of one fraction and 1 in the numerator of the second fraction. The denominator of each would be the same. And at this point, we now have right here a perfect match for transform 20. Okay, so again, we had s plus 3. So we broke it down into the sum of s plus 2 plus 1. All right, s plus 2 plus 1 gives you back the s plus 3. So as I said, this one now is a perfect match. Can you see it here at the very top? Yeah, it's a perfect match to number 20. So we're going to go with that. And I guess the hope is that this one will then be a number 19. But is it a number 19? Oh boy, more complications. If it's a number 19, then remember we have b equal to 3 right there. We should have a 3 on top, and we don't. We have a 1 on top. So we're going to have to make an adjustment to this fraction now. So let's just keep this one the same for now. It's perfectly ready to perform the inverse transform. But what do we do here? We do this. We want a 3 on top, and we don't have a 3 on top. We just plop it there. We can do that as long as we compensate with a 1/3 in the front. Okay, again, quickly check. 1/3 multiplied by 3 will give you back the 1. Okay, so now we have right here, this part right inside the bracket is a perfect match now to number 19. You can see it here, okay, because we have the required 3 in the numerator. So right here, we have a number 19. Okay, we're ready to use our pages to perform the inverse transform. So as soon as we get rid of the s's and we start writing down t's, we have to change the left side to little f at t. This one is a perfect number 20. So what do we write down? We write down this. E to the negative at cosine bt. Of course, using our same a and b values. Perfect. Now we're here. So we're going to have plus 1/3. So the third is the multiplier. And now we do our number 19 inverse transform. So right here, e to the negative 2t sine of 3t. Just like that. So that's pretty great. This one really is kind of demanding to be common factored. So we'll take the exponential function out. And it can look like this. All right. All right, so these are challenging, right? They're a little bit like puzzles. The important thing is that you begin with the denominators, match up the denominators, then start worrying about the numerators. Okay, let's continue on with our next problem. So the next one I wanted to do with you is this one. It's problem 26. Okay. So take a look at that denominator, see if we find anything like that here. Okay, now it's two binomials multiplied together. One of them has an s and the other an s squared. So do we see that anywhere? This is two binomials, but both have s of degree 1. Same, no more. So we don't have this denominator anywhere. So what do? Well, we do have this denominator on its own, s minus 1. That would be here. Okay, it can be treated like an s plus a. And this denominator, s squared plus 1, where do we have that? S squared plus 1 is this guy. Okay, it can be treated with s squared plus a squared. So we've got each individually. So this tells me that I want to split this into the sum of two fractions. Okay, so we are going to split it into the sum of two fractions like this. In one fraction, the denominator will be s minus 1, and in the other fraction, the denominator will be s squared plus 1. We're going to have the sum of the two fractions. Okay, because if you think about this, if we were going to add these two fractions together, the very first thing we would do is form a common denominator, and this would be the common denominator. Okay, but now we have to figure out what the numerators here are going to be. And the fact is we have no idea what those numerators will be. The only thing we can state with certainty is that the numerator here will just be a number, constant. And the numerator here would be something linear. Something of this form, b times s plus c. How do we know that? This is called using the method of partial fractions, and it was part of Math 1431. In fact, it was the last unit of Math 1431, which means that it was post-pandemic. And it means that I have videos on these methods, so I can provide you with those links if you need to review this. But the key is this is a linear term, so the numerator will just be a constant. This is considered a quadratic term, and therefore the numerator is linear and is of that form. So what we have to do next is figure out A, B, and C before we can continue. How do we do that? Well, we take the original numerator, which is 3s plus 1, and we set it equal to A multiplied by s squared plus 1 plus bs plus c multiplied by s minus 1. So in other words, we're saying if we move to the common denominator, then a would be multiplied by this denominator, bs plus c would be multiplied by that denominator. Then you might remember here we would start by substituting the roots. So what values of s can make these denominators equal to 0? Well, right here, s equals 1 would make this denominator 0. So that's what we begin with. We substitute s equals 1. It's called the root. Okay, so let's substitute s equals 1 into the left side. And what will we get? 3 times 1 plus 1 is 4. And what about substituting 1 into the right side? We're going to get a times 1 squared plus 1 is 2. Plus, we're substituting s equals 1, so this would be b plus c times 0, right? So plus 0 here. So 4 is 2a plus 0. If 2a is 4, then a is 2. Okay? So now we know that this fraction has a numerator of 2. Are there any other roots? Is there an s value we can substitute to make s squared plus 1 equal to 0? No, there is not, because s squared cannot equal negative 1. We're dealing with real numbers only. So this means we've used up all of the roots. So you might remember that at this point, we look at coefficients of s. Okay, what is the highest coefficient for s? That would be s squared. So let's look at s squared throughout the equation. Start on the left side. Well, there is no s squared. So that means the left side is 0s squared. What about on the right side? Where do we have s squared? Well, we have it here. This is a times s squared. We also would have it here, plus b times s squared. So the right side is a s squared plus b s squared. Now we divide all the terms by s squared and have the equation 0 is a plus b. Remember that a is 2. So this means we now know the value of b. The value of b is negative 2. Okay, so now if you are enjoying the coefficient method, you could look at another coefficient now, for maybe the coefficient of s, for example. Or, since we know 2 of the 3 letters, we can instead substitute an arbitrary value for s. So I'm going to arbitrarily substitute s equals 0. Okay, so it means you can substitute any number you like at this point, right? Anything. That's what arbitrary means, except for s is 1. We've already used that up. The easiest thing to substitute is s equals 0. So on the left side, what am I going to get? 3 times 0 plus 1. On the right side, what will we get if we substitute s as 0? Well, we're going to get a times 1 plus, substituting s as 0 will make this c. And in here, substituting s as 0, we're going to have negative 1. Okay, so we get a times 1 plus c times negative 1. So that's this equation. 1 is a minus c. Don't forget, a is 2. So we end up with c is 2 minus 1. Or c is equal to 1. And now we have all 3 values, so we go back and we write out f at s in that form here. So we're going to have 2 over s minus 1 plus, now bs plus c becomes negative 2s plus 1 over s squared plus 1. Okay, so we use the method of partial fractions in order to work out these numerators here. And now we're ready to use our chart. We gotta find these guys in the chart. We already figured out that this one right here, where can I put this? Up. Can you see all that? Let me just see. Yeah, we get the whole thing here. That's good. This one we've already established is right here, okay? We're not worried about the 2 in the numerator. We know we can adjust that, make it a 1, okay? So we've got a number 3 that we're gonna head towards here. What about this one with the s squared plus 1? Remember that's here. Okay, which one is it? Is it this one or this one? Here's just an s, here's just some number. Oh, looks like we have both. So we gotta split this again. So we're gonna split that one. So we'll have a negative 2s over s squared plus 1 and a 1 over s squared plus 1. Like this. Okay, so we took this one and we just, since we had a sum in the numerator, we put negative 2s here and then plus, and the 1 is here. Okay, and now we're gonna set these up exactly the way they need to be in order to have a number 3 right here. This one, we're gonna head for a number 5. And right here, we're heading for a number 6. Okay, so again, we're trying for a 3, a 5, and a 6. Now, what's the value of a? For number 3, this says s plus a. So it actually means our a value is negative 1 for this one. Okay. What about for this one? S squared plus a squared. So a squared is 1. So here we just have a is 1. And the exact same thing for number 6. Okay, s squared plus a squared. So a is 1. Now we gotta fix up the numerators, okay? Number 3 should have a 1 on top, so I'm gonna move the 2. Number 5 should have an s on top only, so I'm gonna move the negative 2. Number 6 should have an a on top, but remember a is 1, so it's already set. Okay, so final adjustment time. Okay, so we made no adjustment to the last one. Here, again, we only wanted a 1 on top, so I just moved the 2 out front. 2 times 1 is 2. Same thing here, we only wanted the s up top, so I simply moved the negative 2 to be a coefficient. Negative 2 times s gives us negative 2s. Okay, and now we're ready to transform. Final moment. F at t is little f at t. So we start with a 2. Now we're doing our number 3. So we write e to the negative at. E to the negative at, but a is negative 1. So e to the t. Minus 2, the next coefficient. Now we do our number 5. Cosine at, but a is 1. So we get cosine t. Finally, plus no coefficient, we're doing our number 6, sine of at, but a is 1, sine t, and we're done. Okay, so, take a look. There's a lot involved here, certainly. As I said, these are rather like puzzles, trying to identify the right denominators and making all necessary adjustments. Okay, I'm going to do one more problem with you This is number 28. And okay, big mess in the top. S to the 5 plus s cubed in the bottom. So that's our first job. Can you find that? I don't see any exponents of 5, certainly. So we start, let's common factor the bottom, okay? We'll make the bottom s cubed times s squared plus 1, okay? The top would stay the same, all of that. I don't feel like writing it, so I'm just gonna cheat and say same top. Okay, so I took out s cubed in the bottom. Same deal here though, right? I don't see, here's something similar, I guess. Look at this one, for example. But this isn't an s cubed, it's just an s, right? Okay, here, this one is even closer, isn't it? But it's only s squared. It's not s cubed, so really shockingly close to this one. But we've got a problem. This denominator is not here. So what do? We use the method of partial fractions once again. Okay, so the question is, how do we treat s cubed? And this, you may have forgotten. It's quite likely you've forgotten that s cubed is treated as the product of s and s and s. And s itself is a linear factor. So s cubed is treated as a repeated linear factor, which means to set up s cubed, you need 3 fractions, one with a denominator of s, a second with a denominator of s squared, and a third with a denominator of s cubed. And then finally, this, I don't have room to write here. Why did I think I have room? Finally, the quadratic factor of s squared plus 1. Okay, so I'm going to move this to the next line, okay? Because there's no room for this. I don't know what I was thinking. Okay, so what are we doing? Again, we're setting up s cubed. It means we're going to need 3 fractions, one with a denominator of s, a second with a denominator of s squared, a third with a denominator of s cubed. And since this is considered a repeated linear factor, up top for each is a single letter. So that's how you would set up s cubed. Okay, and then we have a quadratic factor. Remember that for the numerator, for the quadratic factor, we need not a single letter, but a linear term. So d times s plus e is required in this case, since we've already used up a, b, and c. Okay, so again, a repeated linear factor. If you need to replay the videos from Math 4, make sure you do that to understand why this repeated linear factor requires this treatment. Okay, so now it's time to write out the massive equation. So the massive equation begins with this as the left side. Like that. And now we have to think, what will a be multiplied by on the right side? It only has an s under it, and this is the common denominator here. So it requires s squared and s squared plus 1. Plus sign. And now what about the b? Well, it has s squared under it, but we're moving to this denominator here. We're comparing with this. So it requires one more s and s squared plus 1. On to C. It has s cubed under it. We're comparing with this, so it requires only the binomial s squared plus 1. Finally, plus this term, okay, we need a bracket around it because it's a binomial. This term has s squared plus 1 under it. Comparing with this denominator, you can see that it needs the s cubed here. Okay, so I couldn't even get that on one full line, but this is what we have as our expression. And now we have to start by solving for A, B, C, D, and E. Okay, so far, all of what I'm doing thus far is Math 1431 final unit. Once we have A, B, C, D, and E determined, then we'll do the Laplace analysis that's required. Okay, are there any roots? The only root is s equals 0. So start with that. Substitute s equals 0 in the left side, and you'll get 1. Substitute s equals 0 on the right side, and you're going to get 0 plus 0 plus c times 1 plus 0. Okay, so we can determine immediately that c is 1. So that's nice, that's helpful. But we still have 4 unknowns. So we can only go to an arbitrary substitution when there is only 1 unknown left. So this means we have to use the coefficient method 3 times here. Okay, remember the rule was usually you start with the highest coefficient. Well, that would be s to the 4 here. But let's take a quick look at that right side. Where would we have s to the 4? Right here, a times s to the 4. But also here, look, d times s to the 4. But we don't know a, and we don't know d. So that wouldn't help us at all. So we don't start with s to the 4. What about the next highest, s cubed? Where would we have s cubes? Here, b times s cubed. But also here, e times s cubed. But we don't know b, and we don't know e. So that's not helpful either. But let's go to s squared. On the left side, where do we have s squared? Here. So we have 6s squared equals, where will the squares be on the right side? as squared times 1. So right there, okay, I'm going to mark them with green. So where are the squares? There's 1. as squared plus 1. Where else? Look, not here. That's a cube and an s. But here, cs squared. And here, no, that's a cube and an s to the 4. So we only have 2 places where we'll have a square. Here, as squared, and here, cs squared. So the right side is as squared plus cs squared. Okay, take a look and confirm for yourself there are no other squares. This would be s to the 4. Here, s cubed. Here, s. Here, just constant. Here, s to the 4. Here, s cubed, right? So these are the only places for the squares. Divide everywhere by s squared. And remember that c is 1. And that means a is 5. So now at least we know a and c. And now that we know a and c, we can go and try s to the 4. Okay, so on the left side, what do we have? We have 3s to the 4. I'm going to get another color to identify where the terms of degree 4 are in the right side. Okay, look, right here. A s to the 4. So I'll do this in red, okay? A s to the 4. Anywhere else? S to the 4. Right here. D s to the 4. So on the right side, we have A s to the 4 plus D s to the 4. Like that. Divide everywhere by s to the 4 and we get the equation 3 is A plus D. Remember, A is 5. So what does that mean? It means D is negative 2. All right, so that is looking good. Now we have 3 of the unknowns. 3 of the unknowns. But still we don't know B or E. Okay, if we tried s cubed now, that would have a B and an E. So s cubed won't be any good to us, but we can try the coefficient of s. On the left side, we have 1s. On the right side, where are the s's? Do I have another color? Oh yeah, I got purple. Okay, where are the s's on the right side? Here's one. B times s. And where is another s? There isn't another s. That's the only one right there. You can't probably even tell that that's purple, but that's purple. That's supposed to be a different color to help you out. There are no other s's. So dividing both sides of this equation by s gives us right away that 1 is B or B is 1. Okay, so now we know 4 of the quantities and we can either substitute an arbitrary value, but s equals 0 is already done, so we could try s equals 1 perhaps, or we could do one more coefficient. I might as well do the last coefficient. I'll do the coefficient of s cubed. Where do we have s cubed on the left? Right here, 3s cubed. On the right, where are we going to have our coefficients? I am totally, oh, do I have a black? Black will work. Okay, so where do we have coefficients of s cubed? Well, here's one. B times s cubed. And one more right here, E times s cubed. Okay, so the right side is bs cubed plus es cubed. Divide all terms by s cubed and we get the equation 3 is b plus e. But b is 1, so then e is 2. Okay, so now we know all of these and we plug them into here, okay? So we change f at s so that it looks like this with A, B, C, D, and E substituted. Okay, so I'm going to have 1, 2, 3, 4 fractions added. Okay, with denominators s squared, s cubed, and s squared plus 1. And here we put A, B, C, and then D times S plus E. Okay, so again, first we common factored and couldn't find this denominator in our chart. So we had to take the denominator and split it into all of its parts. And now we did our method from Math 1431 of partial fractions. We now know values for those numerators. And now it's time to look at the chart. Okay, so I'm going to move this way up and get our chart in front of us. There we go. Let's identify where we're going to be in the chart. Denominator of s, right there. This will be a number 1. Okay, what about this? S squared, that's a number 2. S cubed is also a number 2. And what about this? S squared plus 1. S squared plus 1 is these guys, right? But look, S squared plus 1 with an S and the other with an A. So one more time, we need to split this one. Okay, so we got to do that. Okay, so we're going to split this one right here, and then we're going to be ready to begin the process. So I'm going to write this again. I might as well move the 5 for this first one because I know that that's coming. These other ones had 1s on top. And then what are we doing here? We're making it negative 2s on top and 2 on top. Okay, and we did that so that we can use a number 5 and then a number 6. Okay, this negative 2 is going to have to push though when we use number 5, so I should have moved it right away. And same thing with the 2 here, it's going to have to push because we have A is 1, so we should only have 1 on top. So I'm going to do that as well. I might as well do that and then we'll be ready. Okay, I might as well go to a new paper. I'm certainly going to need one more paper. So let me do that. Okay, let me put in my little division lines. Okay, so can you see all that I changed in this step? I moved the negative 2 out front because in transform number 5, it should only be an S up top. See? Okay. And I did the very same thing here because in transform number 6, the value of A should be up top. We obviously have A is 1, so we should only have a 1 up top, so I moved the 2 to the front as a coefficient. Okay, so what is our plan? Remember, this one is a transform 1. Then we have these two are both transform 2s. Okay, but I should identify that the value of n will be different for each. So in this case, n is 2. But in this case, n is 3. Okay, then we have a number 5 right here with A is 1. And inside this bracket, we have a number 6. With A is 1. Okay, so grand finale, change to little f at t, and then write. This one is 5 times the transform of 1 over s. Well, the transform of 1 over s is 1. The transform of 1 over s is 1. So we get 5 times 1 here. 5 plus, what's the transform of 1 over s squared? Well, if we have n equals 2, then this becomes t to the 1 over 1 factorial. T to the 1 over 1 factorial, which is just t. Okay, now we do the next one. We have n is 3. So now we have t squared over 2 factorial. Now remember, 2 factorial just means 2 times 1. So 2 factorial is 2. Now we're here, minus 2, and we're doing our number 5 with a is 1, so we get cos t. And finally, plus 2, and we're doing number 6 with a is 1, so sine t. And that is our final result. So there you go. I'll put that there like that for a moment. That is the full solution. Okay, so obviously these questions are not easy, nor are they brief. I'm going to assign problems to you from your textbook. In fact, they are 17, 19, 23, 25, and 27. And I need you to start practicing this because this is necessary for you to be able to solve the differential equations, which is where this unit is moving to next. Okay, so please, please, please practice this. And if you need to review the method of partial fractions, make sure you do that as well. Again, I will post links to those lectures for you as well. Okay, thanks so much, and I thank you also in advance for your working hard in this unit, okay? It's not terribly easy. It's kind of interesting. Like, I think that they're all rather like puzzles, but you might have a different opinion. Okay, take care, guys.